Hello and welcome to a new very interesting video. This video is about this project here, and this project is a Halloween project. It's called the Advanced Analog Pumpkin Lamp, or in short AAPL. And yeah, now I will explain what it actually is and what it does. So basically what we have here is the main assembly. And this will be connected to a long cable, and on the other end of the cable there will be a pumpkin, which I will show you later. And inside the pumpkin there will be a lamp like this, and there will be a loudspeaker. Not as big as this, it will be a bit smaller because otherwise it won't fit in the pumpkin, but it will be a loudspeaker and a lamp. And also near the pumpkin there will also be this thing here, and this thing is a microphone with microphone preamplifier in it. So the goal of this is then that I can connect a microphone here to the main assembly, and I can also connect a line audio source to the main assembly, and then I can play back music, or I can talk into the microphone and you will hear my voice coming out of the pumpkin, and the intensity will also be reflected with this lamp. So this lamp, the intensity will be modulated by my voice. And I will put the pumpkin outside of the house, and so I can talk to people near the pumpkin. But since I have to hear them, therefore this thing is necessary, this microphone with microphone preamplifier, because this will also be mounted near the pumpkin, and I can connect, and this interfaces into the main assembly, of course, and then I can connect earphones to these jacks right here, and I can hear what the people outside are talking, so I can actually talk with them. So again, I will connect a microphone here to the main board, so I can talk to the people outside, and I will connect earphones here so that I can hear what they are saying, and I can hear it because I have this microphone outside. Okay, so it's a lot of stuff going on here, so I think the best thing is to show you just what it does. In the intro you have already seen that the intensity of the lamp can be modulated, and you have already heard the output of the loudspeaker because there was an audio source, a line audio source connected, so you already know that this works. And now I will show you the thing with a microphone. So I will connect this microphone here to the microphone input of the thing, and I will switch it into microphone mode, so to speak. So to switch it into microphone mode, I have to change the overall gain. I will show you the schematic later, so no worries, you will see what it actually does. But first of all, I have to change the thing into the microphone mode. I've used these PC jumpers right here. So now let me put it into microphone mode. Alright, and now I will connect the microphone to the input. There we go. And as you can see, the intensity of the lamp is now modulated by my voice, which is working pretty great. And now if you want to hear something from the loudspeaker, of course, I just have to increase the volume here, and now you should hear my voice from the loudspeaker. So I will move a bit away so that you can distinguish the loudspeaker and me talking into the microphone better. So now you can hear my voice coming out of the loudspeaker. It's working pretty great, as you can hear. So this is amazing. So I can control the volume, of course, so no problems here. Okay, and there are also these two knobs here, and these two knobs are for controlling the lamp. And basically this lamp here, this knob here, this potentiometer, controls the black level. So let me show you what this is. Basically it's the bass intensity, the baseline intensity, or black level, or however you want to call it. So let me show you what this is. So if I'm quiet now, you can see it's the intensity of the lamp when there is no signal coming in, no voice or no signal from the computer. So I can set it to complete dark, like this. So now now it's completely off when I'm not talking. And if I increase it, now you have a higher baseline intensity, or a higher black level, so to speak. So if you know a bit about television, analog television, then it's the same as the black level of an analog television. Or actually, you can also call this the brightness control, right? So this offset is the brightness control. Okay, and I've also this control right here. So this one here, and this controls the gain of this of the circuit which is connected to the lamp. And this is, if you go back to the television analogy, then it's the contrast. So if I decrease it, now you can see the modulation is extremely weak. Now my voice has not much influence of to the intensity of the lamp. And if I increase this, now you can see my voice has a lot of influence. So it's actually more contrasty, so to speak. So this is what this control is doing. Okay, so here you can see. So again, here we have the black level. Now it's 0, and now it's I can also adjust it in a way so now it's completely on, which is of course not very interesting because there's no modulation going on. But as soon as I start decreasing it, it's working. So this works perfectly fine. So as you can see, the basic functions are there. The loudspeaker is working, the lamp is working. So now to round this off, let me show you the microphone preamp. Actually, to show the thing about this is, so first of all, let me put away the microphone. Okay, so or why not? Let's continue talking into it because it's just great. I've just disabled now the loudspeaker. Okay, the thing about this microphone preamplifier is, since I don't know how far the people are away from the pumpkin, I don't know how high the gain of it must be. So this has to be an automatic gain control, and it has to have a big automatic gain control range, so to speak, because I don't know how far they're away. So if they are a couple of meters away, then this thing has to go up to a very high gain, and if they are near, then it has to go down to a very low gain. So this is the speciality in this thing here. So it has to have a high gain difference, a high range of gain which this thing can have. So to demo that, I will connect my oscilloscope to the output of this thing, and yeah, just and we can see how it looks like. So now I've connected the microphone preamplifier, the output of the microphone preamplifier. Here you can see the microphone, and I've connected its output to this oscilloscope. And as you can see, it's already quite sensitive. So let me put it away. I will put it here. Okay, and as you can see, it's working. My voice gets reflected on the oscilloscope screen. And to show you that the automatic gain is working, I just took a little bit, not that loud, and you can see it still is on the same level. And now I talk louder, and you can see it's still at the same level. And now it's still at the same level. It is not changing intensity. So as you can see, the automatic gain control is working. It's working quite well. So if I go further away and still continue talking, you can see that the deflection is still the same. And if I go even further away, you can see it's still the same. So we have a very good automatic gain control action going on here. So now I come back closer, so we have a very good automatic gain control, and this signal then will be connected to earphones, and with the earphones I can listen now to the people outside. Okay, so as you can see, it's working pretty well. It's working. We have a very good automatic gain control action. And as you can see, the response to me whistling is also pretty good, because it should be a sine wave, and it is. So as you can see, not much distortion is going on here, and if I'm quiet, you can see there's a lot of noise, and this is because this thing is very sensitive and so it picks up the fan of my oscilloscope and the computer in here and other sounds, so it's extremely sensitive. You can hear extremely sensitive. Alright. And this extreme high sensitivity is also what I was aiming for, so it works as expected. Okay, so that's for this microphone preamplifier. And now let's talk a bit about the circuit details. As mentioned before, the entire thing is complete analog and there is no IC in here, so I haven't used any op amp, so it's completely made out of transistors like this one here, and just transistors, resistors, capacitors, and basically that's it. So it's complete analog, and of course potentiometers, right? So where should I start to explain this thing? I would say I start with the microphone preamplifier. So first of all, let me turn it off completely because it's still on, as you can see if I increase the black level. So let me turn off the thing. Okay, so now it's completely off, and here we have the microphone preamplifier. I've already removed the screws, as you might noticed before, so there are no screws in here, but of course I will put them back in afterwards. And here we have it, and as you can see, I have used this aluminum foil here, and this is actually there to shield the thing. Since it has a very high gain, I want to be sure that it catches no interference from mobile phones or other EMI sources of EMI. So therefore I've shielded it with this aluminum foil, so this aluminum foil is connected to ground. And here, if you take a closer look, then you can look at the inside of this thing. And this construction is actually a very interesting construction. It's very often called the Manhattan style, and actually it works that way. You drill islands like this here and this here on the board, and then on these islands you can connect or you can solder your individual components. You can see here's an island, here's an island, here's another one, and so I just have to drill holes where I want an island to be, and then I can solder directly components to these islands, and that way I can construct this circuit. Actually, circuits built that way have also very good RF properties, so this is a good construction method. Let me just show you how the drill for this looks like. And here's the drill that I have used. As you can see, it's a diamond drill, and it has a hole in the middle, and so if you drill on an FR4 board with copper, you can drill in these islands, and this is exactly what I did. So now you've seen that there are a lot of transistors in here and a lot of components, and here of course this is the microphone itself. Here you have the microphone. I've connected this thing actually, this is the power plug for this thing, and this is the microphone output, so to speak. And since I had it, I've used this. It's actually an observation camera cable. So this is a coaxial cable which is actually meant to be used for video, and this is of course just for supplying the observation camera with power, with voltage. So this is 12 volt, and here we have this observation camera cable. It's not the purpose for which it was made, but since I had it, I've used it, and it works pretty well. So this thing has also pretty low output impedance, and therefore it can directly drive the headphones. So on the other side I will connect the headphones directly, so it's just this cable, and then on this main assembly I have the headphone plugs which are directly connected to this thing. There's only a potentiometer in between so that I can adjust the volume a little bit. Yeah, this is the easiest way to build it, so I did it that way. And yeah, now let's jump right into the circuit, so circuit time. So here we are right in LT Spice, as you can see, and this is the microphone preamplifier. So when I'm designing circuits, mostly I draw them on paper, and then I do some calculations. And sometimes I also simulate them in LT-Spice, because it's also a pretty a great tool to check your circuits before you build them. And actually you can also design circuits in here. And yeah, let me show you how this thing works. So this generator is a microphone, and actually this microphone needs a bias voltage. So the capacitor and the microphone, think of it as being one assembly, so it's connected directly to this point, and this gives it a bias voltage. Okay, so actually the whole thing is quite complicated, and to explain it in detail, it would be a video on its own to explain the whole thing. And maybe I will do that, because it's interesting, and it's also interesting to derive equations for it maybe. But yeah, let me get over it very quick. The thing is, we need an adjustable amplifier, so we need something where we can adjust the gain. And for this, a feedback amplifier comes quite handy, because by adjusting the resistors in the feedback loop, I can adjust the gain of the whole thing. Okay, so let's first check out what is actually the feedback amplifier. So here we have this transistor on the input, and then it goes to this configuration. It's actually a cascade configuration later on that, and then we have the output here, and the output gets fed back here to the emitter of this input transistor. So this way it gets subtracted from the input signal, and we have actually a non-inverting amplifier like you can build with an operational amplifier. Okay, so here we have this feedback, and from here to ground we have also first of all, imagine this as a resistor. So if we have a resistor from here to ground, then we have, as I said before, our non-inverting amplifier. So the adjustable resistor in this case is this thing here. It's this JFET. It's a J113. Okay, so this thing adjusts the resistance depending on the output level. So actually, how is this done? So I use the output here, then I connect it to this diodes, which are connected as a voltage doubler. Then I get a voltage across this capacitor and resistor here. So this capacitor and resistor are there for a time constant. So by changing the value of these two components, I can adjust how long the thing stacks at a certain gain, or how long does it takes to adjust to a different gain, or how long does it take to adjust back to its original gain. Okay. And then I use this JFET as adjustable resistor. So depending on how high this voltage across here is, this resistance will change, and therefore the gain will change. So to put it simple, the gain of this thing is actually this resistor plus this resistor here divided by this resistor here. So if this resistor here gets lower, then the gain will increase, and if this resistor gets higher, then the gain will decrease. And in this case, the resistance of this resistor is controlled by the output signal, and therefore it is automatically controlling the gain of the thing. And yeah, so that's this point. Okay, and another thing which is important here is that the whole circuit has a huge open loop gain, which means that if this thing would be 0 or a very low value, then the circuit itself has to have enough gain so that it can still respond to this low resistance with a high output, because this is what I need. I need a very high gain if the people have more distance to the microphone, for example. And how do I achieve that? Actually, I achieve it with this gain stage right here, and there are several tricks in here. So first of all, we have a current source at the collector of this transistor. So since the load of the transistor is now a current source, we have a very high impedance here, and the gain of a common emitter amplifier depends on the impedance that the transistor is seeing. So if the resistor here, for example, is just a 10K resistor, we get a gain of 10K times the transconductance of the transistor, so times Gm of the transistor here. Okay, but 10K is not so much. If I increase the resistor to, let's say, 100K, then I would get much more gain. But if it's just a resistor down here, then I don't have enough bias current, and this would then decrease Gm, because Gm depends on the bias current. Gm is actually the collector current, the bias collector current divided by the temperature voltage. So we have the bias current divided by the temperature voltage. This is 26 millivolts at room temperature. and this 26 millivolts is fixed, but if we decrease the bias current, then of course we will decrease the overall gain of this thing. Okay, but if I put a current source down here, then I can choose a current, for example 1 milliamps, but I still have a high output impedance because a current source ideally has a very high output impedance. Ideally it has infinite output impedance. So this gives me a high gain because I have a high output impedance here, and therefore I have a high gain because high output impedance times the GM times the transconductance gives me a high gain. And there's another problem here, but if I have a very high output impedance here, then this transistor itself has an output impedance. So if this would be only one transistor, then I have an output impedance of this transistor. I see the output impedance of this transistor, and this would also decrease the gain again. So that's why I've used two transistors in a so-called cascade configuration. And basically here on the base here we have the input, and here on this we have a fixed potential. So this is actually acting as a common emitter stage, and this is acting as a common base stage. And the advantage of this is that the whole construct has a very high output impedance, and therefore I can get a very high gain because we have a very high output impedance here and we have a very high impedance seen at this point. Basically you can think of this transistor being degenerated by this transistor, and degeneration gives you a very high output impedance. So this is how this works. Okay, alright. What else do we have? Of course, if we have a low load here from the headphones or so, then we have to also do Darlington or compound pair configuration. In this case we have the compound pair configuration, not a Darlington configuration, just to avoid VBE drop, because in a Darlington configuration you have 2 times VBE and here you have 1 times VBE only. And the other advantage of this configuration is that you have a lower THD, a lower total harmonic distortion of the thing, which is also great. It's inside the loop, I know, but if you can improve things, then you can improve things. Okay, so that's why we have this stage. And of course we need to have a high current gain with this configuration here to also allow it that this thing still sees a very high impedance at this point. So there's no way just putting one transistor here. We have to put 2 transistors to get beta multiplication, because if you put them in this configuration, then the betas of the transistors are multiplied by each other and we get a very high current gain, and therefore we see a very low, very high impedance here, and this is what we want. Then this thing is just a VBE multiplier to set the bias current for these transistors. Alright, so this is how this microphone works. It's my own design and I'm pretty proud of it because it works quite well. It has a high amplification range, and this is exactly what I needed. Okay, so now let's jump right into the other part. Let's jump right into the main assembly, the base assembly. And this thing contains the amplifier for the loudspeaker inside, which is then inside the pumpkin, and it also contains the signal processing and amplifier for the thing that is connected to the pumpkin lamp later on. And then it has also a preamplifier for the line and microphone signal. So let's first of all start with that. So this is the preamplifier for the line and microphone signal. Since a line and microphone signals differs heavily from its level, so the microphone has a much lower amplitude than a line signal has, I need to have some way to select the overall gain of this thing, and this happens here. So if this resistor is connected to here, then I'm in microphone mode, so it has a very high gain, and if this resistor is connected and this disconnected, then I'm in line mode, so I have a lower gain because I don't need much gain for the line mode. Actually, if you connect, this is the input, and if I change between microphone and line, of course there needs to be a switch between microphone and line, between the 2 inputs, because I don't want to mix them together, because then my line source would be connected to the microphone and this could damage the microphone. So actually there needs also to be a switch which allows you to switch between line and microphone. Okay, Great, but how does this thing actually operate? Basically, it's quite similar to the thing which you have seen before. It's the same basic structure. Here we have a transistor which then drives this transistor here. On this point we have the output, and here we have feedback. So this is the same structure. We have this transistor here we have the output, here we have feedback, and here we have the other feedback transistor to ground. So the gain would also be output voltage divided by input voltage, which is now about this resistor here plus this resistor divided by this resistor, but actually not quite, because it is also seeing via this capacitor these two resistors, so you have to keep them in mind as well as this resistor here. And so the gain also depends a bit on the impedance of the source, because of this resistor and then going to ground. So actually this complete construct here is in parallel to this point to AC ground. Don't forget about that. So the gain depends a bit on what is connected to here. Okay, alright, so why is this capacitor here, you might ask? Basically this gives us positive feedback. So if you have a transistor like this and you want to know the gain between its base and emitter, it's most of the time it's 1, but not 1, it's a bit lower than 1, so it's a bit below 1. And this is a very important fact here, because the signal which comes in here is a bit lower than so actually the signal here is a bit bigger than the signal here, and this signal then gets fed back. So if the gain would be, let's see, 0.95, then we have almost the complete signal in the same phase as the input has, fed back to this point here. And this means that if the input goes up, then here this signal also goes up, and the input sees almost no resistance. And this is pretty great, because therefore we get a very high input impedance, which is just great, so that we don't load the microphone much. You have to be careful when building such feedback circuits, such positive feedback circuits, because a positive feedback circuit with gain which has a gain of 1 or more can become an oscillator, because then you have positive feedback or regenerative feedback, so it will regenerate itself. But in this case this is not a problem, because we have a gain which is lower than 1 from this point to this point. But you just have to keep that in mind, that positive feedback will cause oscillation. So if the gain would be 2, then this thing would be an oscillator for sure. Okay, so at the output we have another interesting thing. Actually this is the output transistor, as I've mentioned before, but here we have another transistor. Actually you could replace this transistor with a resistor and it would still work. The only reason for this transistor is that we get a higher impedance, so that this transistor sees a higher impedance at this point, and this is important to reduce THD, total harmonic distortion. Actually the quality of the loudspeaker inside the pumpkin is not that good, so it's a bit over-engineered, but why not doing it? Okay, so let's continue. Now we have two parts. We have the power amplifier part, and we have this amazing signal processing thing here. So let's continue with the power amplifier. So first of all we have a potentiometer which allows us to control the volume, and then we have a power amplifier. The topology of the power amplifier is quite similar to the one of the microphone preamplifier, if you can recall this one here. The only difference is here that we don't have a cascode here, because we don't need it. We don't need so much gain actually. Then we have still this VPE multiplier to set the bias current for the transistors. Down here we have the current source, it's the same configuration, and the feedback network is this here, and this sets the gain with the same equation as I've used for this circuit and for the microphone preamplifier for the microphone preamplifier circuit. So that's it, and on this point you connect the output resistor or the loudspeaker, which then is inside the pumpkin. Okay, so now let's go down here, and this circuit here also has a potentiometer as input, and here this circuit is the signal processing and amplifier for the lamp. So this thing here is the lamp, this resistor here. Actually the lamp has more than 4 ohms, but it was just for the simulation. And how does this work? Actually we have this gain stage here, and then we have this output, this emitter follower output, and the output of the emitter follower is coupled back to the base. So we have also feedback, negative feedback going on here. The reason for this, so actually this does two things. It sets the gain to a stable gain. This is the first thing, and the second thing is that it decreases the output of the emitter follower, because negative feedback decreases output impedances of your amplifier circuit, and this is what I've done with this negative feedback right here. Okay, so here I have my signal, and this signal has a DC offset of about 6 volts. Okay. And now we have to think about what shall we do with this signal. If I just connect this signal directly to the lamp, then I have the problem that if I am not talking, I have 6 volts here, so the lamp will be at mid brightness, and if I'm talking, that then the signal would go up and down and up and down, and there would not be much intensity change of the lamp. So actually what I have to do is I have to convert this voltage to a DC voltage, which represents the volume of my voice. Okay, and let me show you how this is done. But before I show you the thing, how the circuit works, I will show you how it looks like on the oscilloscope, because then you can understand it better. I will probe this point here. I will probe at this emitter of this transistor here, so you can see what the circuit actually does. So let me do that. So as you can see, the oscilloscope is connected of the emitter of the transistor, which I showed you before in the circuit, and now I will show you what these controls actually are doing on the oscilloscope. You have already seen it before, that with this control I can adjust the offset, so to speak, so the brightness of the lamp when I'm not talking, and with this control I can adjust how contrasty it is, how much my voice affects the lamp. And now I will show you what this does on the oscilloscope, and for that I've connected my function generator to one of the line inputs. Here you can see the function generator is now connected to one of the line inputs, and now let me show you the oscilloscope screen. Okay, great, so here we're looking at the oscilloscope screen, because as always, no scope, no fun. Alright, so now let me show you what happens if I adjust the potentiometers. So now I will adjust the potentiometer, which adjusts the offset or the level of the lamp, the intensity of the lamp when I'm not talking. Okay, so let me do that. So if I move the potentiometer, if I turn the potentiometer, then the signal will be moved up and down, so like this. Okay, so let me put it at this position. And if I adjust the gain potentiometer, then the following thing happens. Look at that. The signal gets scaled, of course, but something very interesting and something very beautiful happens now. The signal is anchored at a certain level, at the level which I can set with my offset. So I can anchor it, for example, here at 4 volts. So now it's anchored at 4 volts. And now with my gain potentiometer, I can adjust how big it should be. So it's anchored. It's anchored at this point. So it scales from this point up and down. So this is anchored, and from here it scales up and down. Okay, look at that. Isn't that great? So I can adjust the offset. So now I put it to 0. And here I can scale it from this point on. This is just amazing. Look at that. I really enjoy it. This is my most favorite circuit that I've ever built. Look at that. This is just, is this great? You have the signal with an anchor point, and of course it does not only work with sine waves. So if I switch it to triangle wave, for example, it still has the same behavior, and it still works pretty good. Okay, look at that. Isn't that great? Here now I'm anchored on the 0 line, and I can adjust the gain. It's just amazing. It's just amazing. Here now we have the square wave signal, and I can also adjust it. I can adjust the gain. Alright, okay, so back to sine wave. So here we are back at the sine wave signal, and it's still working. This is just beautiful. I really enjoy it, and I hope you enjoy it too. Okay, so now let's move back to the circuit, and now let me explain how it is doing this thing. Alright, here, so now we are back at this beautiful circuit, And I've already told you that this here is an emitter follower with a low output impedance. But what happens next? What happens here? So here we have a decoupling capacitor, of course. And let's see what happens with this decoupling capacitor and what's going on with the rest of the circuit. So first of all, we assume the following thing, that this is not an emitter follower, so that this is just a diode. It's just a diode connected to ground, because this is the case if this potentiometer, this is a potentiometer by the way, and if this is connected to ground, then we have just a diode which comes from ground to this point. So let me illustrate this just very quickly by inserting a new diode like this, okay, and disconnecting this here. So now we are in this configuration here. We have just a diode here, okay. What's happening now is that if the signal is on its negative half cycle, not on a positive, but on its negative half cycle, then current will flow through the diode and will charge the capacitor in this direction. So normally, if there would be no diode but just a resistor, then the capacitor will charge with positive 6 volts from here to here. Alright. But since now there is a diode here, first of all, let us just neglect the diode drop of this thing, and let us say that the signal at this point, the sine wave signal, has a 5 volt peak voltage. So this would be 10 volts peak, but it has a 5 volt peak voltage. So then this diode, for the negative 5 volt cycle, this diode will connect, and we will have this, the capacitor will be charged with 5 volts in this direction, okay? But it would have been charged with 6 volts in this direction, so there will be a positive voltage of 1 volt in this direction across the capacitor, okay? So what's happening now? If we have a positive 1 volt on here, then we have our 6 volt offset, our signal with 6 volt offset here, okay? We have 1 volt here, so we have 6 minus volt gives us 5. So we have 5 volt offset here, but our signal is 5 volts peak. So the lower point of the signal then will be at the 0 line, if we neglect the voltage drop of this diode, of course. So this will give us, this will anchor our signal at the 0 line. So this circuit, which is also sometimes called as DC restoration circuit, does exactly that. And this is also sometimes used in CRT television or something like that to restore DC voltages. Okay, alright. So, but now what's happening here in this circuit is it can do a bit more. Let's just imagine that here on this point we just insert the voltage source, which has, for example, 5 volts. Then this, of course, would give us an offset of 5 volts. But it has still the same DC restoration, but just with 5 volts offset. And this is what this potentiometer and emitter follower is doing right here. So if I reconnect it like this, then you can see we have exactly that. So if this potentiometer is to ground, we have this diode going up here, and we have this DC restoration going on. And if we adjust the voltage on this point, then we have the same situation like the diode with a voltage source, and therefore we can adjust the offset. Alright, great. And so the only thing that's left is to rectify this signal to get a DC voltage, or basically not a DC voltage because it changes, but we just want to have the peaks. We want to have a peak hold, and this is what this thing is doing with this capacitor and resistor as time constant. And then the only thing that's left is this configuration right here, which gives us a high current gain and a current drive capability to drive the lamp. And that's it. That easy. It's just that easy. It's just 3 transistors doing the signal processing and 2 transistors driving the output. And this is how the whole thing works. So here we have the complete pumpkin lamp again, and this was and this is the explanation of this circuit. Okay, pretty great. I hope you have enjoyed it. Okay, so that's it. So now let us look at the pumpkin in action. Okay, this was a pretty long explanation and you made it through it. So it's time to reward this, and now I will show you the complete pumpkin thing in action. So this lamp thing here has to go inside the pumpkin, and a smaller version of the loudspeaker has also to go into the pumpkin. By the way, the smaller version of the loudspeaker is not made out of wood, it's just made of out of cardboard. That's it. So now let me just rearrange things a little bit and show you the pumpkin. Pumpkin time, yeah, pumpkin. Okay, alright, so here I have the pumpkin, and he looks pretty happy, right? And the lamp is inside now, and the loudspeaker is inside. And now the question is, how do I connect a pumpkin to an amplifier? And I've just built this cable here, and this cable has 3 connectors. One connector is for the lamp, the other connector is a common ground, and this connector here is for the loudspeaker. And as you can see, the lamp has double wires just to get more current through, and the ground has 3 wires just again for more current drive capability, for more current conducting capability. And of course this cable is connected at the back of the pumpkin, and I've just drilled a small hole to fit the cable through it, and this is how it was made. So here we have the cable, and now I have to hook up the thing. One very important thing is that I don't mix up the lamp and the loudspeaker, because otherwise if I do that, if I mix them up, then I could destroy the loudspeaker. So I have to be careful, but I know this is the loudspeaker, and the loudspeaker has to go into here, and the lamp has to go into here, and I need one of the grounds which goes into here. Both of these connectors are ground, and now let's just try it out. So I have to switch it back to microphone mode, so let me do that, because I want to try it with microphone. Alright, so now we are in microphone mode, and let me turn on the power. Alright, so now we are in microphone mode. The thing is now on. I have turned all potentiometers to 0, so just that you can see it from the so just that you can experience the calibration process of the thing. So first of all, let us just check the loudspeaker. So the loudspeaker, now the volume is at 0, and now test 1 2 3 pumpkin test 1 2 3 pumpkin test. As you can see here, my voice is now coming from the pumpkin. So pumpkin test 1 2 3 pumpkin test. So this works pretty well. All right. So this is the first thing, and now the second thing is to check the lamp. So let us first set the black level with this blue knob. Alright, so now we have a certain black level. Okay, so maybe I turn off the lamp here. Okay, so it's better. So we have a certain black level now. And the next step is to adjust the gain of the thing, or the contrast, however you want to call it. And now let me do that. Test, pumpkin test, lamp test. Alright. Look at that. Now, isn't that amazing? The intensity of the lamp is now modulated by my voice, and now you can see the intensity changing, and the pumpkin is talking. Pumpkin talk, yeah, it's cool. It's just cool. Look at that, I'm talking pumpkin thing. This is just amazing. It's the most amazingest thing that I can imagine. Especially thinking that the thing is completely analog and made just of transistors and resistors and capacitors and so on. So it's just great. Okay, so as you can see, the project is a success. It's working as expected. It's working perfectly fine, and I hope you have enjoyed this thing and maybe learned a thing or two by watching this video. And yeah, so this concludes my project presentation, and thanks for watching. Happy Halloween and bye!